Hi everybody. Today I will explain and compare the different types of electrical and electrochemical energy storage methods. Energy storage devices are physical components used to store energy for later use. These methods include but are not limited to batteries, capacitors, and superconducting magnetic energy storage devices. These are the types of devices I will describe today. There is a practical application for each of these energy storage devices, and by contrasting each of their advantages and disadvantages, we will be able to conclude an efficient approach to each application. Electrical energy storage methods play a very important part in today's technology. A battery is a device which stores chemical energy from electrochemical cells that are later used as electrical energy. There are two types of batteries: primary, which are disposable, and secondary, which are rechargeable. Primary batteries are commonly found in portable devices that are to be used infrequently, or while away from a power source, such as an alarm. Zinc-carbon batteries and alkaline batteries are common forms of primary batteries. Generally, primary batteries have higher energy densities than secondary batteries, but do not last efficiently when under high drain with loads under 75 ohms. When not in use, a primary battery usually loses around 8 to 20% of its maximum charge every year at room temperature, also known as its discharge rate. This occurs because the primary batteries contain a part where chemical reactions occur without producing current or having a load. One could lower the temperature of the batteries to decrease the discharge rate of the chemical reactions. Secondary batteries are much more abundant in today's market and can be found anywhere from the mobile industry, cell phone batteries, to the automotive industry, car batteries. Common types of secondary batteries include lead acid, which are the oldest, nickel cadmium, nickel metal hydride, and lithium ion cells. Chargers or rechargers are required to charge a secondary battery. This is done by applying electric current to the discharged materials within the battery to reverse the chemical reactions that occur during use. The discharge rate of secondary batteries varies greatly with the type. Nickel cadmium batteries lose 10% of its charge in the first 24 hours and then 10% a month. They can typically be charged about 1,000 times. Nickel metal hydride batteries have a discharge rate of 15% per year. They can typically be charged about 500 times. Degradation of the battery occurs because its electrolytes move away from the electrodes, or because active material falls off the electrode. Three types of electrical methods of energy storage that will be discussed are capacitors, superconducting energy storage devices. Capacitors are widely used in electronic circuits for blocking direct current while allowing alternating current to pass, in filter networks for smoothing the output of power supplies, and in resonance circuits that tune radios to particular frequencies, in electric power transmission systems for stabilizing voltage and power flow, and for many other purposes. A capacitor is a passive electrical component with two terminals that is used to store electrical energy in an electric field. Though there are many types of capacitors, they all operate by having electrical conductors separated by a dielectric. When there is a potential voltage across the two conductors, an electric field builds up between them. Positive charge builds on one of the conductors, while negative charge builds on the other. Capacitance is the ratio of the electric charge on a capacitor to the voltage potential between them, and is measured in farads. The capacitance is directly proportional to the distance between the conductance plates, being larger when the separation is narrower. Capacitors are used in devices which require power while a battery is being charged. It can be thought of as a temporary battery. Power supplies require capacitors to help smoothen the output of a rectifier and hide current ripples. This application is invaluable across all sorts of power electronics, where a clean power supply is needed for signal and control circuits. Capacitors are abundant in power distribution systems, where their use is to counteract inductive loads created from devices such as electric motors and transmission lines, and make the system seem mostly resistive. This is known as power factor correction. In signal processing, capacitors can be used as memory storage devices. In combination with inductors, one can select information in specific frequency bands. A capacitive sensing system is one where the system would change based on factors that cause the capacitor's structural configuration to change. Field levels in airplanes can be accurately measured since the capacitance increases as the field covers more of the conductors. Devices like fingerprint sensors rely on the pressure or strain measured from using capacitors, and monitoring the distance between the conductors. Touch switches rely on the change of effective area around the plates of the capacitors for operation. Lastly, a superconducting magnetic energy storage device consists of three major components: a superconducting coil, a power conditioning system, and a cryogenically cooled refrigerator. The cryogenically cooled fridge would cool the superconducting coil to a temperature below its superconducting critical temperature. The superconducting coil can then use its flow of direct current to generate an electric field to store energy. Under these conditions, the current will not decay, and the magnetic energy could be stored indefinitely. With the use of an inverter or a rectifier within the power conditioning system, you are able to discharge the coil and release the stored energy back into the system. Using a superconducting magnetic energy storage device is the most efficient method of electrical energy storage. The method has an efficiency of over 95%. Also, the method has a very short time delay between charge and discharge cycles. Very high amounts of power can be outputted almost instantaneous for a short amount of time. Also, because the system is motionless, one can deduce that it is very reliable. Mainstream use of superconducting magnetic energy storage devices are limited by its extremely high cost. A mechanical structure is required to hold down very large Lorentz forces created by the coils. Also, it requires a lot of land to install a commercially viable SMES device, a loop of around 100 miles. It is very hard to manufacture the superconducting coil because the material is so delicate, and the lengths of the superconducting wire required are longer than usual. Through this, I have described the importance of both electrochemical and electrical energy storage devices used in today's market. Much of our technology and devices rely on these energy storage methods to operate. The methods range greatly in terms of the date in which they were developed, the practical applications, their advantages and disadvantages. Batteries, capacitors, and superconducting magnetic energy storage devices were described. Batteries, though the oldest method, are the most commercially used method of electrical energy storage. They have a wide range of applications, are relatively efficient and cost efficient. However, they are limited in lifetime and not environmentally friendly. Capacitors also have a wide range of applications. They have an unlimited lifetime, but suffer due to not being able to hold on to energy for a very long period of time and have a smaller capacity. Superconducting magnetic energy storage devices are very efficient and can discharge and charge almost instantaneously, but are very expensive both in terms of manufacturing costs and land required to operate. Thank you for listening to my presentation. That is all.